И мы продолжаем наш хардкорный трек. Следующий наш докладчик Вojin Jovanovic. Звучит, согласитесь, почти как по-русски, Иван Иванович. В GraalVM довольно много людей с научным бэкграундом. И Vojin, один из них, у него PhD в Computer Science. Вообще в этом проекте, в чем его прямо сила, что там делается довольно много наукоемких экспериментов. И в отличие от других научных работ, все эти научные эксперименты, по большому счету, в Computer Science, они прямо сразу же внедряются. Утилита Native Image до сих пор носит статус экспериментального, но несмотря на этот статус, очень многие в Java-сообществе пробуют ее применить сейчас, и можно прямо сказать, что это прямо утилита у всех на слуху. Vojin один из непосредственных разработчиков этой утилиты, поэтому у вас есть уникальный шанс получить знания о нем, как говорится, из первых рук. Итак, Vojin Jovanovic про GraalVM Native Image. Hello, Vojin.
Hello. How are you doing?
Yes, we will talk about GraalVM Native Image today, and I noticed that it is quite common in Java community to make equality between GraalVM and GraalVM Native Image utility. People really think that GraalVM is all about ahead-of-time compilation, ahead-of-time native compilation. Are you happy or sad about that?
I'm personally, I'm working on a native image project, so I should be happy with that, but I'm actually not, because I think GraalVM is like much more than GraalVM Native Image, right? I think that it brings quite a bit of other things. For example, like all the other languages that it speeds up and makes them interoperable with each other. I think actually that's probably the biggest thing that GraalVM brings. But essentially, I think that the world is just not. It's kind of a new paradigm. So it will take a bit of time until this picks up. But for me, I think this is the biggest power of GraalVM. But native image is also really cool. So and it's now very popular, which makes me headsex while fixing bugs and all that. But so in a sense, GraalVM is not native image. That's what I would like to say. I think GraalVM is way more, and I think it would be great for the whole community to understand the powers that it brings, and that like never writes a binding for a library in another language again. That's what I would say.
Great. So we can start. Your talk, Vojin.
Okay, thanks for the great introduction. I enjoyed it, actually. Understand quite a bit to it. So I'm a researcher and manager at Oracle Labs. So I basically work on GraalVM for about 5 years now, and I've been like in all parts of the projects, from the core stuff to the UI stuff. I'm basically UX stuff. I'm essentially the guy that kind of I have two faces. One is trying to make stuff right. So I'm kind of pushing for the compatibility of native image quite a bit, and I'm like very particular that everything should run exactly the same as Java. So and then I also try to make it faster and smaller. So essentially I do two things. I'm a researcher, and I'm working as a manager of an engineering team, and I do also quite a bit of engineering, actually way more than research. So and yeah, you can find me on Twitter at this link. Right. So just for those that don't know what GraalVM is, I think this is probably the best picture we can have, and that's essentially that you take any of the popular languages, right, which you can see on the top, right, including Scala, Java, Kotlin, and JS, Ruby, R, so on, Python, very important, and the whole C ecosystem via LLVM. And then what we do is we do this automatic transformation we just wrote interpreters for these languages, right, and then we have this automatic transformation from these interpreters into compiled code, and because of that we have like a relatively simple way to specify languages, right, which is written in Java in the same framework called Truffle, and then then all of them get like compiled with the Graal compiler, right, and then the second part of the project is the native image, right, which essentially takes the all of this Java code and basically produces like an assembly for any architecture you know, any popular architecture, let's say like that, right? So there is more being added basically. And then, you know, we've embedded like applications in quite a bit of places. So, you know, we have the OpenJDK running standalone. We have an Oracle database which just got released called MLE, where you can essentially run all of these languages in the Oracle database as a part of a stored procedure. Then we did a MySQL experiment back in the day, which is currently paused, but actually quite well functioning, and you can build standalone apps and Node.js. Okay, so basically it's, you know, I think this is for the first time that you can run all of the important languages in the same framework. You can add in the same runtime. You can add new languages relatively easily, and basically then deploy them, you know, in standalone or as a shared library in some of the projects normal architectures. Right? And at the core of this project is essentially the Graal compiler, right? So that's how the whole project started. So and essentially, I think it's worth mentioning why is it so important, right? And the first bit is like, first it's done with a really cool team. It's, you know, it's lovely working in this team, and they've kind of taken a fresh approach to writing compilers. So it was written in Java, and it was written with a very in a very modular and maintainable and extensible way. So it's kind of kept minimal. So it also has this visualization tool, which kind of helps quite a bit with working. It's really addictive and joyful to work with this compiler, which is usually not the case with many compilers, because you have to like parse logs, and, you know, it's always clunky, right? With Graal, it's just pure joy, right? And then the compiler comes in like two flavors. One is like the community edition, which is completely open source. And the other one is the enterprise edition, which contains many advanced optimizations, right? And that's essentially where Oracle is making a product, right? So and that part contains many advanced optimizations. Many of them are also published, and like the main ones are probably like partial escape analysis and then clever duplication of code and inlining, right? And then, of course, there's many other peephole optimizations as well, right? So it's a quite an undertaking, right? And what you get from that is like what you don't get from other compilers is that essentially, if you have a very abstract program, for like this stream example on the right, effectively behind the scenes, like the duplication decisions will be made in such a way that that you always kind of take a right path in inlining, right? And take this like very abstract example, which has like, I don't know, 10 layers of abstraction in each of these functions, and you basically execute this in you convert this in a very simple loop, right? And you get essentially the performance, almost the performance you would get in C, right? And when we look at what this brings is essentially you can see that for essentially older like style of code, like if you look at, I don't know, spec JVM. So here on the x-axis, basically just before I start, on the x-axis we have the the benchmarks. Some of them are benchmark suites like Renaissance, Da Capo, and Scala Da Capo, spec JVM. But then we also make another cross-section just for people that use a certain type of workload. For example, for Spark and for data processing, then we just took Scala and Java. So these are and numeric Java. So these are basically kind of slices in the space of benchmarks, right? And you can see here that essentially whenever you have a lot of abstractions, which is how we write most of the code these days, right? You will get like performance like boost from like 42% or like 36%. It's basically between 30 and 45%, right? In some benchmarks, it's even 2-3x, of course. This is a geomean across a large set of benchmarks, right? But this is basically what all of these advanced optimizations give you, right? The places where they're not good, as good, is basically, for example, something like numeric Java, right? So because there you can, there's not so much smart things you can do, basically, right? So it's hard to bring more, and you can also see this on Da Capo, which is written in this old style of coding where you have like large functions with while loops and whatnot, right? So basically, this kind of gives you a picture of essentially what Graal gives you, and you can yeah, and these numbers are actually getting better every year. So I know in the last year they jumped 10%, right? So that's I expect even more probably 10 more. So essentially and yeah, so if you're running anything modern like Renaissance or like Spark or any kind of data processing, you basically you can expect at the moment about 1.4% speed up. This is with the Graal Enterprise Edition. With the Community Edition, you will be better on these. We will be better on these essentially benchmarks with a lot of abstractions. But then on some of the benchmarks they will be worse, right? So that's Community Edition. But this is also climbing over time. So and then one thing we did in the past 2 years is also like Graal was written in Java, right? So it had this very big problem with startup essentially. And one of the things we do is we use the GraalVM Native Image now to compile the compiler into a shared library, right? And then we use it as a extra JIT compiler in Hotspot, right? And this is packaged as native image. And essentially, when we do this, you can see on the right that essentially all of the stuff is, before we would wait 2,000 seconds for the first iteration. Now you wait 191, right? Which is basically about the same you would wait with C2, right? But then, of course, you get way better numbers later, right? And one very important bit to mention here is that, like, with latest Java versions, like, if you get the Oracle subscriptions for Java, you also get GraalVM Enterprise, right? So it became like a part of a standard offer. Yeah. So, okay, and now like let's talk about the native image part, which will be the biggest part of the talk. And essentially here now we take Java code, right? Only Java code. We cannot still ahead of time compile JavaScript code, but not at the moment. And what we do in native image, it's basically a tool that AOT compiles Java and makes a snapshot. So I will explain that. So essentially what you start is with like your application, your libraries, your Java library, and with the substrate VM, which is a VM written in Java, which underlies the whole, it's kind of a GC and all other stuff that comes with it. And then what we do is we do something called points to analysis, but we do it in an iterative way. And compared to other points to analysis, we do another thing, which is initialize parts of the Java code at build time, right? So we have this algorithm that kind of figures out what you can initialize at build time, not to affect the semantics of the code, and then we run all of these initializations, and then we make a snapshot of the heap, right? And then we do this iteratively until the fixed point is reached to kind of see, we make something called a closed role assumption. So we figure out what is reachable from this application. And another thing we do is for all of the reflective stuff we take essentially we take a configuration file at the moment which essentially tells you which parts are reachable reflectively, so that the analysis knows about them. So that essentially, once you run your program in runtime, given the right configuration, it runs exactly the same as in regular JIT. And then we make this kind of two things. One is like two object files. One contains the object heap, right? That's all the stuff that got initialized at build time and then snapshotted, and then you get the code. And with that, you essentially you basically you produce either the executable or the library, right? So you can make either a shared library, so you get just a pure SO file with entry points, or you get machine code, or you get just an executable that you can run, right? And essentially, how does this why is this so important? And this is like for cases where startup matters, right? So we'll start in order. One of them is the shell applications, right? So for example, if you take a Scala C and then you just like this, which is a Scala compiler, you have a hello world.scala, and try to time it, it takes like 70 milliseconds, right? And then we build a native image of the Scala C compiler. We time it with hello world, and you get like 5 milliseconds, out of which most of the time is actually spent in spawning the process and all that, right? So it's operating system stuff. And that's really cool, right? So if you want to have like snappy applications, especially UI applications, for example, remember this splash screen in Eclipse with native image that would take like 10x less, right? And many others, right? We are actually now trying to build Minecraft to see, to kind of remove the progress bar completely from the thing and make a demo out of that. Right? And then another very important place where this matters is essentially microservices. And microservices and serverless computing, right? Because there you kind of want to have a flexible cluster where you can freely turn on and off your instances, right? And this here, what we see is like a graph in the startup time of native image, and then compared to like JDK 8 and 11 on the popular microservice framework, which are like Micronaut, Quarkus, and Heliden, right? And you can see that they're of different weight both, but essentially whenever you do a native image, you'll get like more than an order of magnitude improvement, right? So from like 1 second to 35 milliseconds, and this is only for one request, right? If your application is kind of big, right? So for example, something like a very, very large microservice with many hundreds of methods or service like sub-services that can be called. Every one of these first requests will be very slow, and essentially with native image you get just like a predictable performance, right? The first one will be a bit slower, right, because of the operating system load some memory pages in, but that's negligible. So essentially you get predictable performance from the get-go, and you can then that allows you to scale up and down your cluster way faster, essentially. Right? So yeah, and then also when you look at the memory footprint, right? So what happens here is like when a JIT compiler runs it, essentially it spawns like an interpreter. Then the interpreter loads all the bytecode and verifies it. Starts collecting profiles, runs the JIT compiler, and this is a very, very, very heavy on memory, right? So if you take a first request on these frameworks, you can also see that essentially that we kind of we save a constant of about like around like between 100 and 50 megs, right? So essentially for every service you have, you will use less memory, hence you have to pay less bills, right? There is also, of course, some savings on the payload itself. So if you have a very large application with a humongous heap, we do some optimizations there as well, but that's not the topic of this talk. Our PLDA paper just got accepted for that. But essentially, we will, in addition to this, we will have a smaller footprint at runtime as well. One part of it is like that we have smaller objects, and the other one is that we do some tricks with object inlining. So basically, yeah. And now for performance, right? It's kind of commonly known that ahead of time compiled code is not as fast as JIT compiled code, and the reason is the profiles, right? Because in the AOT mode you typically don't have the profiles, so what we do here is basically, well, you have to run twice, right? So what we introduced is this profile guided optimizations in native image, which are currently only Enterprise Edition feature, and basically. You basically run the native image with this PGO instrument first. You get an instrumented binary which you run with the relevant workloads, and then you get the profile files which are then basically converted with there's PGO flag into the optimized binary. And when we do this, the numbers are actually quite good, right? So what we get is like this is a benchmark for the Quarkus Hibernate benchmark, and you can see that like the first 100,000 requests are basically, the number of handled requests per second is way bigger with native image, right? So you see that in native image you kind of have almost a flat curve, while on the JDK you need to serve like 100,000 requests to reach the peak performance, and then only you get to the same performance, right? And there is quite some research happening into making, like, I personally believe that this line should be strictly above this line, because essentially in the AOT mode you have way more time to think about optimizations and as a compiler, and you can collect arbitrary profiles which you're like not allowed to do on hotspot, right? You just have a limited set of profiles. So I personally believe actually native image will be not only smaller and better startup, but faster, right? So yeah, but there is of course a downside, right? And that's that you have to build your native image, right? So this requires, because we'll talk about this in the end of the talk, but yeah, it requires extra effort in some cases. So now let's talk about another part, which is essentially now we showed you can use for regular Java apps. Essentially, you can use native image. That's cool, right? But another thing you can essentially build from native images. You can build shared libraries, right? And then these shared libraries can do interop with the C code. And how the C interop is essentially is made is that you can essentially from pre-existing C code you can call Java from C, right? You can also call C from Java in the new C interop code, and then you can always from this interop mode you can always call all of the pre-existing Java code. So essentially, what this does is it makes a link between the native world and the Java world that you can from the C++, C, Rust. You can call any library you have in the Java ecosystem, which is vast, right? Yes. And then how do we do this? Is we have a bit of extra types that we introduced, right? Because the Java types are not the same as C types. So what we do is now we essentially have to support row memory access and pointer arithmetic. And this is essentially not an extension to the Java language. We made it as an API that just fits in Java. It's based on intrinsified functions and on annotations, right? And then, of course, we have a special type that you model for pointers, which we call word. And this word type is essentially, you can have different kinds of it, right? So one of the like you can, for example, for void star, you do just a pointer, and then you have unsigned for size t or signed for s size t in C, right? And for example, you can see how you could implement like string len in Java here, right? You take a char pointer and then you just write you write something that seems like Java but actually produces like C-like code, right? And okay, so and then essentially this is kind of the mapping between annotations and in the interoperability, and we have these like C function, C constant essentially. So the C function is essentially picking up the function from C. You can take a constant, which it has a definition in the C files. We have a struct for all the C structs, and then a pointer to for any pointer. And for example, this is our int pointer, but you can of course define your own, and so on, right? So you can make a pointer to a pointer, and of course you can include stuff, right? And you can have like link libraries, like require libraries, right? So essentially with just annotations and Java code, we can do most of the operations you can do in C, right? The only thing we cannot do is return a struct, and we cannot like pass a struct, right? So without a pointer. So these are the two things we don't do, especially but it's also doable. And another thing we don't do is the C++, but there is like an open project for that. So once a good master student or master student probably shows up, we should do it, right? And this is like for example, how we use system Java to implement our nano time, right? So we'll get like we'll allocate a stack value, and then we'll do a size of .get in Java, right? And then it'll call the clock get time, which was defined above, and then you can do in the structure that it returns, which is this TP, right? You can do multiplication, which looks like Java, right? So in Java, this is a bit clunky still. It's not as ideal as something like written in Scala, but it's quite usable. I think we wrote a lot of things in this interop, and then especially because you need it for implementing the JVM part itself, right? And of course, you can use this interop from any language, right? So at the moment, not many people use it, but like you essentially can use Scala as well and Kotlin, right? So this is really like from any JVM language, you all of a sudden you can build like entry points, you can call into C code, you can get structs from the C code and so on, right? So good. So yeah, let's look at this little demo that I prepared, right? So here I have essentially so I prepared the project, right, which it's better here from Visual Studio Code. So I prepared the project which contains like several projects, right? So we have what I did is like said, how can we bring one of the cool libraries from the Java ecosystem into C? So let's say you have a native project and you want to do for example, like sentiment analysis, right? And of course, in Java, there is this OpenNLP, which is a really cool library, and you want to use it, right? And of course, this example can be used on any library from the Java ecosystem, right? So and then if we come here, we see that essentially in the C code we will have a main.c, right? What we have is we load two like tweets and prices. What we want to do is we want to correlate like some tweets to the stock market prices, right? And essentially how we do it is like we say, okay, so this is our project. It can be like a database or anything you write in C, and then you just write a simple C function, right? That you call, and this C function is like included in this lib sentiments, which is produced by GraalVM. So the GraalVM, when it builds a shared library, it also produces an H file where you can essentially where you kind of expose all of the entry points, and this is how it looks. One thing that you have to do is you have to essentially give your own thread to the virtual machine. So whenever you start, you need to create this isolate, what we call an isolate. It's essentially attaching a thread to your machine, right? And then what you can do is basically, and then of course in the end you have to tear down the isolate. So tell your virtual machine that this thread is not longer in use. But besides that, it's very simple code. You just pass this one thread, and then you get essentially you can call any function you want from your Java. So and if we go to Java, right? So if we go to Java, we can see that like we have the C interface part, which essentially, for example, we have the C entry point, which is used to produce this correlate tweets with market, right? And now this is the bridge to this interrupt part, right? We have C char pointers, we have this isolate thread, which is basically a trisolate, and then we have type conversion utilities, and then you get back to Java, right? And you see that here, for example, this one can be also called from essentially Java itself, of course, right? Because it's a very simple example, but in general, you can like, test in Java, but then you can also build a shared library from the same code. Okay, and here I won't go too much into details, but basically at this point, what we do is we use typical Java stuff, right? So to do this in C++ as well would be quite extensive, right? So in a sense, this is also a way to kind of slowly port your C projects to Java if you want, right? Because you can kind of start rewriting parts of C in Java, and it will just work fine, right? And that's also how some people use this, right? So basically, so we'll here take the streams, like to do the typical like tuples of prices and feed sentiments, and then we will do this sentiments analysis. And just for fun, I did this sentiments analysis in another language, which is essentially see where it is, Scala, right? So all of a sudden we take a Scala, and then we have, I think it's here. And then you have like again here like Scala code, so you can use any project you want basically. And finally, what we did is like for just to show that it can run all the languages. We have this parser of JSON. We use this Kotlin parser because I kind of find it convenient. And so we made the tweet parser and the price parser, right? And now when we compile this, right, you will see in this folder we have like the data, right, which is the tweets. We can what we have here, for example, tweets, right? So it's JSON, and then we'll use this project to parse this, right? So let's do a compilation of this project. So now we compiled everything with Java C. So and then, as we've seen in the first slide, we now produce basically jars, and then we build native image. Because native image builds a whole world, essentially, it kind of the compilation time it takes a bit longer than what you would expect with Java C, and that's probably one of the biggest downsides at the moment of native images, because you essentially you have to in Java people are used to kind of compile relatively fast, but here now you have to compile your Java project, and then you have to compile it again to native code, right? And for this program that uses like OpenNLP, you can see it takes like on my laptop it takes about like 30 seconds or something, 40 seconds, right? So and actually we are currently working on speeding this up. So here I'm building two things. One is the library, and one is the standalone executable, right? Because what we want is essentially I want to show linking to the C code and running this directly from yeah, running this directly as a Java program, right? So let's, yeah. Cool. So now we produce this standalone binary, which is just like, as produced with C, right? And we can run it, and it will collect the sentiments, right? So this is collecting some tweets about, I think it's some cryptocurrency, which is again popular. This was written in 2017, you see, but it's again popular, I guess. So it's making it's checking if Twitter tweets are do they correlate to the market data, and on some days they do, on some days they don't, right? So it's kind of not quite predictable, right? But in general, it's a low correlation, right? And now we can see what happens. We can go to the C project, right? And here, for example, this could be your whole project written in C. You can see that we in main C, how we call it is essentially it's just like a function, right? Correlates with the market, right? And we pass the files that we read. And here we can essentially again compile. We have this like library, so it's lib sentiments dynamic lib. And then we have this lib sentiments.h. If you look at the lib sentiments.h, there will be essentially, you will see that we have some extra stuff, but then you can also do correlate tweets with the market, which is a pure C function, right? And now we can essentially with this we can essentially let's compile it, and then we do sentiments, right? And what we get here is now from your C project, you get exactly the same functionality. So basically, so what you get is the whole Java ecosystem right there in your native project, right? So cool. And now what we did is this, like to make, so this was completely AOT compiled, so no JIT compilers whatsoever involved. But we also made this lib polyglot.so, which essentially which builds an API towards all of the languages, right? And it builds such an API that you write once, and you can then embed any other language. If you write against this API, you will essentially you can run Python code from your C, you can run JS code from C, Ruby or R, right, or any incoming language. So you kind of write once and you're done. Any language that comes is there, right? And this is particularly interesting for like projects which use some sort of scripting for either for their customers or for the users, right? So for example, what we experimented in the past was like with MySQL, Postgres, Oracle, Apache, and Nginx. And there we kind of build such an we use this lib polyglot to kind of run user JavaScript code in a big C project, right, or native project. And of course it supports all of the debugging and profiling. So once you embed this, you get like you go to the Chrome debugger and you can debug any of your languages, which is also very nice. And these languages have exactly the same performance as when you run them in the JIT mode. So there is no difference. Maybe like module bugs, but there is like I think there's not many of them left. And this can be really used for the wide range of applications, right? So kind of this is but one note here is like all of these languages will be interpreted and JIT compiled. So if you include lib polyglot, it can be big, right? So it won't be as slim as the previous stuff I've shown with the tweets. Okay, so and then in the last 2 years also we kind of together with Gluon we've pushed towards pushing Java essentially to iOS, Android, and to kind of desktop applications, to like UI applications as well. How we do is we essentially we kind of have two ways of compiling code. So one way is essentially because there is so many different architectures, right? We don't want to support just the phones. We want to support RISC-V, all funky micro architectures. And for that, what we did is introduce the LLVM backend. So we have the GraalVM Native Image, which compiles to LLVM, and then essentially you can compile to any architecture. And what's really cool is that essentially adding a new architecture is quite a simple task, right? So if you would want to do RISC-V here, it wouldn't be much of an effort. Basically, by following this link, you can see the instructions, but it's around like maybe a couple of hundred lines of code. So it's measured in weeks as opposed to months or even years to implement the proper backend, right? And actually, you get quite good performance. So at the moment, one downside is that, for example, the LLVM support for garbage collection is still experimental and quite slow. So when we run LLVM, when we run AMD 64 with LLVM and ARM 64 with LLVM, we actually only AMD 64. We get kind of worse performance, right? And so that's why we don't use it for that. But for ARM, actually, you get better performance. And that's it. So you essentially, if you want to run any of this code on your specific architecture, right, you can do it with LLVM in a matter of like weeks. And what we are doing now at the moment with a collaborator called Microdoc is we are essentially supporting the ARM 32, and that's work in progress. It takes a bit longer because the whole Graal was built for 64 bits, so it's actually not the LLVM part. It's the making code work with 32 bits part. And then now we have like, okay, so now we have like all of this we mentioned, we have it running on all architectures, right? So that's really nice. And what we need to do is like also get a kind of UI. And for that, if you want to write a pure Java project, what I would suggest is like JavaFX. I think in the Java space, it's probably like the best UI. And here the Gluon essentially provides a way to deploy JavaFX and regular Java apps on iOS and Android, right? And then like what Gluon provides here is essentially many other integrations. So you can have a Java API towards like Bluetooth devices, accelerometers, and all these devices in a kind of platform independent way, which is what Java was all about. Right? So and it all really comes with an IDE. So you treat this as a typical project. You would just write like normal Java code, and then you essentially use JavaFX and you build an app with Gluon tools, and via GraalVM Native Image, it will be deployed to your device, right? So and this is kind of necessary with Native Image because Apple doesn't really allow dynamic code on iOS devices. And you cannot use the Java interpreter; it's way too slow. So basically, Native Image is at the moment, I think, the only way that it can reliably deploy Java on iOS, right? So essentially, what we do here is we also pull in all of the iOS specific parts of the operating system, and that's how we fuse this. Like in this first diagram of Native Image, we basically instead of like Java for Windows, we just add a new platform. And there is a PR underway to we are trying to push this towards mainstream Java, but this is probably going to take a while, right? I think for that we need to pass like all of the tests, which I'm going to talk about later. So iOS and Android there, right? So, and of course, like this, as I said, you develop this as a typical project, right? So you have a Maven and a Gradle plugin, and you do JavaScript compilation followed by the native image generation, followed by linking, which is required for OS-specific tools. And then you do the signing. It's all handled by the plugin, and you do deploy to your iOS devices and simulators as well as the App Store, right? So it's kind of a one-stop shop to work with mobile devices. And also one cool thing here is that you can also use the desktop app, right? So if you write they like the desktop app will work equally well on iOS and on Android as well. So to show that, I will basically I have an app here which is essentially we build this chat app which is this like showing how well JavaFX works, and also shows some downsides, but it's like actively worked on. So if you look at this, it's just a typical project, right? We have a pom.xml, and it has some extra stuff which come with this plugin. So for example, you will include some services, or you will use this Gluon attached to basically get like a cross-platform access to a camera, images, keyboard, and so on, Bluetooth, right? So it's just a typical project, right? And then we can run it as a Java project, right? So we just say Maven JavaFX run like subproject app, right? And you will see that we get voila. So we get this like chat app, right? And so, for example, like we can like right? We write the message, and this goes via, and we can also like do things. It's a demo, right? It's not a full-blown chat, but we can like upload images as well, right? So yeah, so it's just like a desktop app, and now it also uses one cool trick. It's basically because whenever you have a mobile app, you have to manage your own cloud service. It provides something called the cloud link, where you can essentially, where you can directly kind of without managing a whole service communicate between your device and the cloud, right? And that we can see that, for example, now I will like use the same app, right? Which you would essentially you would build it by just saying here find compile, right? Dash the iOS, right? And this will compile the app for iOS. And you can also natively compile it, of course, for desktop as well. Whoops. Here. I don't know why this failed. It's very strange. Yeah, let's do a client compile. Doesn't matter. I have a version on my phone already running. So now I will switch to the phone view, where essentially on the phone view where we can, yeah, here it's building now. So we can switch to the phone view, which is on another Zoom. And I will share my screen to just show that this like app. Right, so we have a shared screen. So now we go to test flight. So this app was deployed actually to the App Store. So just see. Here we go. And you can see like, you know, hi snow one, and you can see the image, right? So basically, right, and this will now be transferred to the desktop. So essentially, you get the same look and feel that you had on the desktop, and which is what is really cool. You can essentially also develop. You can also develop on your desktop and not have to like use your phone during development all the time because it's a cross-platform UI. Okay, so the compilation here, did it finish? Yeah, this is going to take a while. So because it's a quite a big app. And then let's get back to the presentation. So what are the things to be done here? One thing that we have to do is allow creation of iOS and shared libraries directly by GraalVM Native Image. So currently we use Gluon tools for that. And this is important because we want to kind of allow Java code to run in any mobile platform, basically, right? So you can take any library from Java and just plug it onto mobile. And then we want to kind of strictly define the parts of Java that are supported, because this was currently just put together. As you can see, it runs very big apps. So I've seen games like this SpaceFX runs on a mobile. I personally built this contact tracing app back in February last year. Yeah, even before others did it, but then I just let them to complete the job. And essentially, I used Java for contact tracing. It was a breeze. But what we didn't do is we didn't formalize this, right? So we need to kind of say we need to take a subset of Java and then say this is supported, pass all of the tests that are relevant for that, and then mark others as unsupported, or maybe even pass it all. That's like a management decision. We'll see. But for example, should we support AWT on a mobile phone? I personally am not sure, but let's see, right? So, and then we are also working in minimizing the binary size, because the binaries are kind of still big now. So we are actively working on like various optimizations for that. And then one thing that I would like to see is like a Java interpreter on mobile for development. Again, student projects welcome, where we would use just like an interpreter that we just released in GraalVM called Espresso, which is an interpreter for Java. And we should essentially, on a phone, you wouldn't have to wait for the image build every time. You could just use this interpreter to run your code on the phone. And then once you're done, you just build a final image and ship it to the App Store. So this is it for mobile. And then like what's like, it all sounds great and easy, right? But there is pitfalls with native compilation, as I mentioned at the beginning, right? One is that the Java's ecosystem is kind of reflection heavy, and on the right you can see like just one bit from Netty, from this class called Platform 1, right, where you do all kinds of like all kinds of reflective access, and then there is like there is ones where you go like a conditional inside of a conditional. If this throws an exception, then try that. And these are kind of quite annoying. So a user that like a project that uses a lot of reflection should kind of tell native image what's being used, right? As one way to do this is essentially we have this native image agent where you can run, for example, your whole test suite, and it produces the config, like the config needed that tells the image generator what to produce. It gives it out from your tests. However, there is like this global configuration bloats images quite a bit, right? So you, for example, for Netty, we just did this. So it said let's support Netty out of the box. We ship the config together with Netty, and then like the image size. I did this pull request, and then all of the parties like Spring and Quarkus and others, they were like, no, this is too much, like 4 megs, no way, right? And essentially, and then one more problem is that debugging these configuration problems is very hard, because as you see here, many times if you try a reflective thing, actually no such field exception is expected, right? So then this will handle the code and just do a different thing, and that's exactly what you don't want. You don't want your project to basically behave differently with the native image. So what we are working on now actively, and this is our main focus, because native image is really nice at the moment, but to really gain traction, we need to kind of make it as easy to use as any other part of Java, right? And for that, right, what we are doing is we are building this predication-based model for configuration, right? And this model will have 3 phases of the same model. One is annotations that you will put on a code, or potentially a language feature. We'll see about that. And then the second one is config files, which we have already just modified. And the last one is basically the features, which are you can also call them like compiler plugin. Feature is a native image compiler plugin. And then we want to improve the agent as well, which is essentially running your code to produce the configuration and to generate the predicated version of configuration. This is a research project that we're working on at the moment. Essentially, you just run your program, and how this would work is you would use your manual config that you want to kind of hand tune. You would say what's your domain, for example, io.netty, and then you would run your whole test suite with the agent to get the correct configuration. And since this is predicated configuration, it means that it will include reflectively only the stuff that might get called from a certain point in the code, right? So it won't include all of the reflective stuff you ever could call, right? So it kind of makes like a subset of the stuff you really need, right? And then another research project that we want to do here is to essentially take this and the project source, and then we feed it to the annotation generator so that you can like out of the box get your annotated project source. Because external config is nice, but basically if it's not in your source code, you're never going to maintain it, right? Without some special ID support, but I wouldn't go there. So essentially, we are working on that. So generating these annotations, and then we want to do also debugging. Like when you make a mistake with configuration, we want to do this via fatal failure. So we want to add a special mode where you can basically just run with an agent, run your native image, and then see if, with a fatal error immediately as the config fails, and know what you need to include extra in the config, right, while debugging. And one more thing we're working on is this third-party configuration repository, because for legacy projects, we will have to, you cannot expect every project to adopt these changes immediately. So we are working on something like a TypeScript repo, where essentially you can, like community-driven support to port the whole Java ecosystem to this model. And this is kind of our plan to kind of fix the last remaining issues, so that native image is really a first-class citizen in the Java ecosystem, and that that basically everyone can use it without much hassle. Because at the moment you still need some effort to basically get your larger projects to work, right? So you can run all kinds of small projects, like for example Scala C and stuff like that. It's already a breeze to run. But then some bigger things I tried, like Neo4j, for example, that was still a challenge, and Minecraft, right? So it requires still some user hustle. So we are working. This is the plan to fix this. And that concludes my talk. That's about it. So I'm kind of looking forward to the questions.
Hi, thank you, Vojin, for your great overview of GraalVM Native and Image and GraalVM, etc. Yes, we have some questions, not so many, so please, audience, please ask your questions in chats. It's a great chance to get answers from Vojin. And first question is about GC, garbage collector that can be used when you transform your application in GraalVM Native Image. The question if you can use J1, ZGC, CMS, etc. with GraalVM Native Image.
Excellent question. Yeah, in these benchmarks, actually, the GC is one of the bottlenecks, especially for like microservices. But so you can use G1. You can use G1 at the moment, but only in the enterprise edition. So G1 is an enterprise edition feature that we developed, right? So in the community edition, there is like a simple GC, and Alibaba has introduced, like, it was a simple serial GC, but then Alibaba introduced like kind of survivor spaces. So it's basically a very simple copying GC with survivor spaces, which I'm actually surprised for how many applications it works just fine. But if you wanna run a seriously big application with a lot of GC pressure, you at the moment need an enterprise edition.
Okay, but you said that you have G1 in Enterprise Edition, but I believe it's not the same G1 that is implemented in Hotspot. It's re-implemented in Substrate VM, right?
Yes, it's parts. Big parts of it are rewritten to fit because there is many little details. Of course, it's a complex beast, right? But in the core algorithm is basically the same.
Okay, core algorithm is the same. Okay. And another question about native image heap. The question is, what if current time is written into field during class initialization? Will native image have the time of OET compilation in that field?
Yes, that's a very good point. It's not only the time, there are worse things. For example, random seeds.
Yes.
Right? So yes, so by default, native image won't do such stupid things, right? Because to get time, you have to go into native code, and that we don't know about, right? So we won't initialize anything that's going into native code. So the original native image was actually built only for these truffle languages, so it would work in databases and such. But then we had to extend it. So there was like a large effort to remove this assumption and then say, we don't initialize by default, right? So initialize only which we are certain that it's safe. Now what happens in the community is that many people like this gun, right? And then they like start initializing everything at build time. And then this is really, some people like it, but I'm like strongly opposing it. Like, you should do that only if you exactly know what you're doing. And basically, as far as I've seen from what's happening in the community, most of the people don't know what they're doing. So basically, yeah, these kinds of things happen, right? So really, my advice here is like this: initialization and build time can be a great optimization. You can burn in like whole config files and whatnot at build time so that your application really starts instantly. But you need to know what you're doing, right? So if you start like initializing stuff around, bad things happen, right? There is a lot of assumptions about initialization. For example, all the superclasses of the initialized object also have to be initialized, and so on, right? And you must not keep open files running threads and all these kinds of things you must not leave them in the heap, right? So it becomes an exploration in a sense, and it's not an out of the box experience which we are striving for.
Okay, and as I guess build time initialization is off by default now, right?
Right. We have a proof algorithm which proves most of the. So we do it for the JDK ourselves, right? And that makes a huge difference. it proves like at the moment, I think it proves like more than 50% of the classes, I would say, right? And it proves it as safe for initialization, right? So it will actually initialize much of your code, but then the code that goes into system properties, like anything native code related, is like off the shelf, right? So that you have to do yourself, and then I'm actually considering making a flag that will say, if you do that, don't come for help, really, because it's like because the number of issues that we get that people they did something wrong there is like there is also another thing people like to use is these substitutions. So they start and substitute Java code, and then I get bug reports. And then someone debugs it for 4 hours and sees that someone did a wrong substitution. So these are really, you need to be careful with these. And we actually made a mistake by making it way too easy, I think, right? We should have made it, harder to do, right?
Okay, great. Thank you for your answer. And we have also another question about your C interop with C. As far as I understand, you have alternative approach for C interop in compare with normal Java. You have your own interface, your own API, etc., etc. Is it correct? So
Yes, it's our own, basically. It's our own because we have this concept of isolates, right, which Java doesn't really have, and we are really just a shared library, right? So in a sense, yes, we developed our own because it was really hard to fit this into any kind of JNI, right? And also it's kind of very rare that you call Java from C, right? It's mostly in JNI, in JNI, C knows about the Java types, and here we are more about Java knowing about the C types, right? So it's a bit, I think, and it's partially historical reasons, but I think actually it's a good decision because we have this concept of isolates. So what you can do is you can without any effort make an additional VM, so you can run parallel VMs, which is very useful, for example, for like Nginx. You can run every request in a completely separate heap, which gives you isolation, and all these things were not in JNI, right? So we would not be able to do that, and that's and the second thing is it's very low, it's kind of low profile, right? It's really a library. I mean, it will have a GC and all that, but it won't like hijack your signals and stuff like that, right? So it's kind of, you can really treat it as a C library, and yeah, the fact that it has a GC inside, it's not so bad, I think. So yeah.
Okay, great. But you also look at Panama project where they also would like to move implement the same idea that Java should know about C, not C about Java.
Yes, that's true, and we should probably at one point unify that, right? So, but it was when we did this, it was very long time ago, right? So basically,
Panama?
Yeah, it was kind of starting together, I think, and then I think the communication was not the best, and then this happens in computer science all the time, like people doing the same stuff even within the same company, right? That's sometimes even office to office, right? So that's like, but yeah, we'll see. I mean, this is not necessarily if Panama becomes really a de facto standard, we should probably just implement that and be done with it, right?
Okay,
but then we should probably, that's a good point. We should probably like see that Panama can support these isolates, right? Because
yes, maybe.
Yeah, it would be. I think it would be valuable that because these isolates are really, really cool, and they have a place in this space. Yeah, with them you can, besides security and that you can isolate different things, you can also kind of for example, throw away a whole VM relatively cheaply. Without even doing a GC, right? So you can do these like one-off requests and stuff like that. So that they have a space in the world, and I think Panama should support them. And then a unified API would probably be the best solution, right? Why two things for the same thing, right?
Okay, and I believe the last question: people who would like to use your C-interop, do you have utilities for automatic, like G-extract for automatic wrapping C libraries?
Unfortunately not, right? There is like a plan to do that. So there is like a long-term plan to do, like probably reuse what Panama does. And also what we plan is to do the same for C++, right? But this is a long-term goal. So that's a very good question. Yeah, we should probably, like, we are kind of at the moment, we're really, the whole team is more or less fighting with kind of making it easier to use native image and essentially making it easier to use and fixing all the kind of bugs that stay from the past period. So, but in the future, yes, we should definitely do.
We have only 5 seconds. Thank you very much, and continue in discussion zone. Please ask him in discussion zone. Thank you.
Thank you so much for hosting me.
Thank you, Vojin. It was great. And yes, now you should have Zoom link where you can meet other people. And
excellent.
Who will ask you, I believe, will ask you many questions.
Okay. Thank you so much.
Thank you. Thank you.
Bye-bye. Bye-bye.
Bye.